In section 5.4, we're going to look at the mean and standard deviation of a binomial distribution. Now, we've talked about the mean and how to calculate the mean and standard deviation for a probability distribution in general, but it turns out if we know that we're dealing with a binomial distribution, the calculations for the mean and standard deviation are much, much simpler. So suppose we flip an unfair coin 5 times. Now we're going to say it's unfair because the probability of getting ahead is not 50%. Suppose in this case it's 60% or 0.6 probability of landing on its head. Now let's create a probability distribution. So just like in the previous section, we'd have to consider the situation where we'd get 0 heads, and plugging 0 into our probability formula for x, and in this case n will be 5 again, the probability of getting 0 heads, if there's a 0.6 probability of this coin landing on its head, is 0.01024. And we do this for the probability of getting 1 head, for the probability of getting 2 heads, on and on and on, to the probability of getting all 5 heads. If we wanted to calculate the mean number of heads that would come up, we have a formula for that we saw in section 5.2. The sum of each of these x's times the probability of x, and then adding all of those up. That is, the mean equals the sum of x times px for each x. However, if we know that this is a binomial probability distribution, and in this case, assuming that it meets the 4 criteria for a binomial probability distribution, and it does, then we can forgo the more difficult calculation and multiply n, which is the number of trials, times p, which is the probability of a success on 1 trial. It turns out that that calculation will be the exact same thing. So in this case, there were 5 trials, and the probability of a success was 0.6, so we'd have 5 times 0.6, which equals 3. Now keep in mind, as we go through this, that we can only use this formula for the mean if we know this is a binomial probability distribution. If it's another kind of probability distribution, or we don't know what kind of probability distribution it is, we'll have to use this original mean formula. 0 times 0.1024 plus 1 times 0.0768 plus 2 times 0.2304, etc., 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 all the way down, and adding all that together. But if we know it's a binomial probability distribution, use this simpler formula. Now we'll find the standard deviation of this binomial probability distribution. So if you recall, we had 2 different formulas that we could use for the standard deviation of a probability distribution. I'll focus on this one mostly during the semester. That is, the standard deviation equals the square root of the sum of x squared times px minus the mean squared. However, if we know that this is a binomial probability distribution and not just any old probability distribution, we have an easier formula to calculate the standard deviation. That is, it will be the square root of the number of trials times the probability of a success times the probability of a failure, or again, 1 minus the probability of a success. So in this case, there were 5 trials, the probability of a success was 0.6, and then that means the probability of a failure is 0.4. Multiplying all these together, we get the square root of 1.2. Plugging that into the calculator gets us that the standard deviation was 1.095. So again, keep in mind, this was much easier than squaring the x, multiplying it times the px, adding those all 6 of these rows up, and then finally subtracting off the mean squared. Now, since we knew it was a binomial probability distribution, we could simply take the square root of the number of trials times the probability of success times the probability of failure. Much easier. So let's look at an example. So suppose we flip an unfair coin 8 times. The probability that this coin lands on heads is 0.3. Find the mean number of heads expected on 8 flips and the standard deviation of the probability distribution. So since let's double check that this is would result in a binomial distribution. Are there a fixed number of trials? Well, we're flipping a coin 8 times, so yes. Are the trials independent? Again, coin flips are independent from one another because the probability of a head coming up on one flip is unaffected by any previous flips. Would each trial result in only one of 2 possible outcomes? And again, yes, we'll either get a head or a tail. And lastly, is the probability of getting a success, or a head in this case, the same in each trial. And it's going to remain 0.3 in each trial. So yes, this would result in a binomial distribution. So that means we can use our shortcut formulas for finding the mean of the distribution, or the mean number of heads that would come up. So that is n times p, or in this case 8 times the probability of success 0.3. That will give us a mean of 2.4, or the mean number of heads we should expect to come up on 8 trials is 2.4. Similarly, we can use our shortcut formula for the standard deviation. The square root of n times p times q is the square root of 8 times 0.3 times 0.7, which comes out to be 1.296. Most values of our probability distribution will fall within 2 standard deviations of the mean. That is to say, the maximum usual value is the mean plus 2 times the standard deviation, and the minimum usual value will be the mean minus 2 times the standard deviation. Let's look at an example. Suppose we flip an unfair coin 8 times. The probability that this coin lands on heads, we're going to say, is 0.6. Find the mean number of heads expected on 8 flips and the standard deviation of the probability distribution. Then let's find the maximum usual value. Well, the mean, since this would be a binomial, would result in a binomial distribution, we can use our shortcut formula and find that the mean is 4.8. So we have a mean number of heads coming up, it's 4.8 heads. The standard deviation will be our shortcut, using our shortcut formula, 1.92. So the maximum usual value is the mean plus 2 times the standard deviation, or 4.8 plus 2 times 1.92. So 8.64. Now if you think a little harder about this, what we're saying is that if we got any more than 8.64 heads, that would be unusual. Well, certainly in this situation, since we're only flipping the coin 8 times, that would be very unusual to get more than 8.64 heads, or in other words, 9 or more heads. We simply can't do it. But that goes to show you that the maximum usual value calculation is correct. Suppose we also wanted to calculate the minimum usual value. Again, use our formula mu minus 2 sigma, or the mean minus 2 times the standard deviation. And here we'll get 0.96. Now what this is saying is anything less than 0.96 would be unusual. 1, we would not, in other words, if we got 1 head, we would not call that unusual. But on 8 flips, if we only got 0 heads with this unfair coin, that we would call unusual, because 0 is less than 0.96. Suppose we take a separate coin and change the probability of it landing on a head. So still an unfair coin, but we're going to have a lower probability of it landing on heads. And we're still going to flip it 8 times. So this is still going to result in a binomial distribution. Again, let's calculate the mean number of heads. In this case, 8 times 0.1. The standard deviation then will be 0.849. And the maximum usual value is the mean plus 2 times standard deviation is 2.498. That is, if we got more than 2.498 heads out of 8 flips with this coin, that would be unusual. So 3 heads would be unusual if there was only a 0.1 probability of a head coming up. The minimum usual value is negative 0.898. We could safely say that if we got less than 0, this would be unusual. But of course, we can't get fewer than 0 heads. So there is no minimum usual value in this case.